Hello and welcome. We are going to evaluate properties of a bunch of states using the PC model. The PC model is discussed along with all other thermodynamic model in chapter 3 of the textbook, and you can learn more about different models in this chapter. Also, properties are discussed in chapter 1, and chapter 0 introduces overall what a state is, the basic concepts. So even before we begin, we have an idea of these states. At a high pressure of 20 MPa, we are supposed to find a bunch of state. State 1 is a saturated liquid state. State 2 is a saturated vapor state. 3 is a superheated state. And 4 is a subcooled liquid state. And then we're asked that what if the pressure is reduced to 100 kPa? Of course, the state should translate to something like this as the pressure is reduced. And finally, we are asked to find the critical state, which should be here. That's our state 5. And state 6 and 7 are supercritical state, that is at a pressure even higher than the critical pressure. So we expect 6 and 7 to be somewhere like here and here. Okay, so let's launch a suitable app. Notice that we are interested in thermodynamic properties only here, so therefore we can use either the flow state app or the system state app. So first of all, this particular video assumes that you have already taken a look at the SL model video. In this example of 13 minutes video, I have gone over the rudiments of how to calculate a state. And doesn't matter what model we use. In this case, we're going to use the PC model. The look and feel are exactly identical. You'll see the same kind of layout in every different model. Okay, so having said that, so let's begin. State 1, 20 MPa supplied. Temperature, is saturated liquid, which is quality is 0, so that's pretty simple. State 2, same pressure. And it's saturated vapor, quality should be 1. State 3 is superheated vapor, again same pressure, and temperature is supplied to be equals T1 plus, T2, which is same as T1 plus 100 degrees Celsius. Notice all these arithmetics are done in SI units, so really I'm adding 100 Kelvin, and adding 100 Kelvin and 100 Celsius are same. The difference in temperature in Celsius and Kelvin are exactly identical. Finally, state 4, pressure equals P1, and it's a subcooled liquid. T1 minus 20 degrees Celsius, I believe, was given to us. So we have found all the states, and you can see that the subcooled liquid phase has been computed as part of the solution of this state. Okay, so now let's go to the graphics panel, and we are in for a surprise. Notice that how state 4 is on the saturation line instead of being on the subcooled. This is the liquid zone. This is where we expect the state 4 should be. Why is that? That's because it is a TS diagram, and entropy of a subcooled liquid is a function of temperature mostly. Almost is the simpler submodel uses the assumption that entropy is a function of temperature alone. As a result, state 4 is on the saturation line. Had we plotted, instead of a TS diagram, say a pH diagram, you could see that state 4 is not sitting exactly on the, because enthalpy is a function of pressure and temperature as opposed to entropy. So going back to the TS diagram, even there, then why book after book repeats that the state is to the left of where we see it? Well, if you pan on it, just drag the mouse over the calculated states, and it kind of zooms into the state. If you keep doing that, you'll see that state 4 is really not exactly on the saturation line. So this hairline daylight that you can see between the state and the saturation line shows the origin of why we draw the TS diagram as we do like this, just to exaggerate the subcooled liquid zone. Okay, let's go back. Now, the next question is, what if the pressure was 100 kPa? How will that, so all you have to do is to go back here and say, okay, P1 is 100 kPa, recalculate state 1, and instead of going to every state, just click on the super calculate button, and all the states have been recomputed for constant pressure of 100 kPa. As you can see, the entire bunch of states have moved down. Finally, how do we calculate the critical state? What are the two properties we can supply? Well, first of all, notice the quality, the x equals 0 line is our saturated liquid line, and x equals 1 is our saturated vapor line. But y is volumetric quality. It's another kind of quality, where x is the mass-based quality, mass of vapor divided by the total mass. Y, on the other hand, if you put the pointer over on the bottom, we'll see the definition. It means how much volume of vapor divided by the total volume vapor. So if I set y to be 1, that means I'm saying it's saturated vapor, and when I say x equals 0, I'm saying it's saturated liquid. So these two lines intersects, obviously, at the critical point, and we should be able to get state 5 as our critical state, as you can see. And the phase is shown here as critical state. Finally, state 6, what is known is that these are supercritical state, 50 MPa. Pressure is higher than critical pressure, and what is given is temperature is 500 degrees Celsius. So notice that it's called, so it's 50 kPa 500 degrees Celsius versus, I'm sorry, it's 50 MPa 500 degrees Celsius. So that's why, okay. And finally, state 7 is same as 50 kPa, P5, P6, I'm sorry, and temperature is given 300 Celsius. Oh, again, I made mistake. Okay, that's fine, equal. So if you go back to the graphics panel, so 5 is my critical state, and you can see that state 6 and 7 are supercritical vapor and supercritical liquid states. So I think I've covered all the different zones, except for H2O, you can even find the state of an ice if you put a temperature less than 0 degrees Celsius. So this bottom part is solid phase. So this particular model covers the solid phase too. So I'll stop here and let you explore to find out that finding properties is made so simple by these simple tools.